Section 4.2, one-to-one functions and inverse functions. So first off, let's recall what a function is. Remember that a function takes an input and goes to an output, but specifically a function is a relation in which the domain values do not repeat. Visually, if you see the graph of this, it passes a vertical line test. That is, take a vertical line that goes forever in both directions, run it completely across the graph. Do you ever touch the function in more than one place? And if the answer is no, then you do have a function. If we check this thing out, notice that it fails the vertical line test and thus is not a function. So a circle is not a function, not at least via our definition. Now, a one-to-one function is using a similar idea, but it's actually going to deal with the fact that the range will also not repeat. So what that means is that every element in the domain and in the range is unique, and so every domain element goes to exactly one range element. If you were looking at the graph itself, graphed on an xy coordinate plane, a function has to pass the vertical line test, and if it's a one-to-one function, it will also pass a horizontal line test. That is, do the exact same thing, but take a horizontal line, pass it over the entire graph, and ask yourself, does this function ever touch my line more than one at a time with a horizontal? So let's determine whether each of the following is a one-to-one function. Notice that here I have these people connected to these people on the right. And so if Bob is connected with Deborah, Dave is connected with Carla, John connected with Dawn, and Chuck connected with Phoebe, the deal is that these things don't repeat. The x values do not repeat. Also notice that the y values do not repeat. And so this is a function, more specifically a one-to-one function. Now notice here, if we have Bob connected to Carla, Dave connected to Deborah, John connected to Phoebe, and Chuck connected to Phoebe, notice that the first thing we see is that our domain values do not repeat. So it is a function. But then ask ourselves, do the y values ever repeat? Well, John goes to Phoebe and Chuck goes to Phoebe, and so it is a function, but not a one-to-one function. Then let's check this one out. 2 goes to 6, -3 goes to 9, 4 goes to 6, and 1 goes to 10. If you're asking yourself, is it a function? The answer is yes, because the x values never repeat. But if you want to know, is it one-to-one? Well, look at the y values. Well, notice that 6 repeats here and here, which means this is not one-to-one. Then we want to play this game of, is this function one-to-one? Well, notice that it passes the vertical line test, therefore it is a function. But then you ask yourself, is it one-to-one by playing this horizontal line game? And so take a horizontal line that goes forever in both directions and drag it up the graph and ask yourself, do you ever touch the graph in more than one place? And the answer is no. And so this, yes, is a one-to-one function. How about this one? Notice that we'll pass the vertical line test, so it is a function, but then notice that if I take a horizontal line and I pass it through, this touches it actually in 3 places here, so this is not one-to-one. Then again, -2, 5, -1, 3, 3, 7, 4, 12. First, let's make sure this is a function. -2, -1, 3, and 4, it's a function. Then let's check and see if it's one-to-one. 5, 3, 7, and 12. None of those y values repeat, so yes, this is one-to-one. Inverse function. So if you're trying to find inverse functions, all you need to do is interchange the x and the y, that is, swap the domain and range of a one-to-one function, and then solve for the other variable, and you have an inverse function. Now, notationally, we're going to write the inverse as f with a -1 power. Be careful because it's not a power. We read this as f inverse. That's how you read this statement. This is f inverse, not a negative power. So watch out for that. Now, if you're looking at the graph, it's true that the graphs are inverses when you reflect them over the y equals x line. And so we'll look at some of these. And also note that the domain of f of x will become the range of f inverse of x as long as these functions are one-to-one. But that one-to-one is required for that to be true. And the range will become the domain of f inverse if you're looking for these things, but once again, only if it's one-to-one. So here we want to find the inverse of the one-to-one function. We're going to state the domain and range of the inverse function. Well, honestly, all you have to do to find the inverse is take the arrows and make them go the other way. That's it. But if we're looking for the inverse function, f inverse of x, the domain of this is just going to be the outputs of the original function. And so the domain of f inverse of x is 10.51, 12.98, 33.38, 81.84, and that's it. So that's the domain. But notice that's because that was the range of the original function. Then, if you want to find the range of f inverse, the range of f inverse is, of course, the domain of f of x. And so that's just going to be the set of the inputs of the original function, which is 30, 40, 50, and 60. If we're trying to find the inverse of this one-to-one function, the inverse of this function, or the inverse relation, will be swap the x's and y's, that is negative 6, 4, 9, 5, 15, 6, negative 14, 7, 1, 8. Then, if I want to find the domain and range of the inverse function, then the domain is going to be negative 6, 9, 15, negative 14, and 1. And the range of the inverse will then be 4, 5, 6, 7. And so the inputs and the outputs swap, that's all. If f is a one-to-one function and f of 2 is equal to negative 3, then inverse of negative 3 has to be what? Well, if this is the x value for the function f, and this is the y value that corresponds to that x value, then all you have to do is swap them around. So that is, now for the inverse function, the input being negative 3 has to give you 2. Has to. But that does rely heavily on the fact that it's a one-to-one function. A one-to-one function f has a domain from negative 4 to infinity, including negative 4, and a range of negative infinity to 0. Then the domain of f inverse is going to be what? Well, it's going to be the range of your original function. So it's going to be negative infinity to 0. And then the range of f inverse is going to be the domain of the original function, and so that's going to be from negative 4 inclusive up to infinity. All right, so now we want to talk about what does the inverse of a graph look like. Well, I said that if you take a graph and you reflect it across the line y equals x, that is this line, what are you going to get? Well, you'll get its inverse. So we just want to reflect each one of these points across that y equals x. Now, if you were able to hold here with your finger and hold here with your finger and flip this across and look at the backside, you would be looking at the inverse function. So think about it like that. But I'm just going to have to move the points. Well, negative 3, 3 is on the line, so its inverse point will be there as well. Well, then notice that I've got this point right here. Well, this point right here reflecting across the xy line is going to have to be here. Then I've got this point 1, 2. Notice that if I reflect it across this line, the mirror image will be here. If I have 2, 5, and I reflect it across this is going to be right here. Now really remember, if we're double checking ourselves, all we have to do is swap the x and the y ordered pair, and that's going to give us the new point. So let's confirm that. This should be the point 5, 2. We'll notice that it's 1, 2, 3, 4, 5, 1, 2. Perfect. This should be the ordered pair, 2, 1, and notice that's exactly what it is. Notice that this is the point negative 1, 0. Sorry, it's way over here, negative 1, 0. That means this should be 0, negative 1. And it is. Then this one should be negative 3 and negative 3 should swap, and of course that's exactly what that is. So then this graph is the graph of the inverse of that blue one. And so I did it visually, but you can also do it via the ordered pairs as we just did. Well, I went ahead and found the graph, so I kind of did this backwards, but now let's actually find these values f of negative 3. Well, f of negative 3 we see is this point, so the output is negative 3. F of 2 is the point 5. The y value pops out. Then f inverse of 0, because I've already got the graph, well, f inverse of 0 is going to be 0, negative 1. In other terms, you should be looking for the y value of the original function, which is right here, but that of course gives us negative 1. F inverse of negative 3 two ways to do it. Either look at the graph that I found or look at the original point. This one ends up being the same, but -3, the input for the original function, gave us -3. If you swap those around, the input being -3 gives us -3. Now algebraically, if we're trying to find the inverse, what should we do? Well, first off, call f of x y. Then you're just going to swap the variables x and y. For every x, call it y. For every y, call it x. Then you're going to solve for the new y, and then you'll call that f inverse of x. So let's do this. First, let's determine whether the function is one-to-one. And in general, a graph is the safest way to figure out if it's one-to-one. And so if I were to do a quick sketch of 4x minus 5, 4x minus 5 looks something like this. But that is a one-to-one function, so yes, it's one-to-one. Then if I want to find its inverse, step 1, rewrite f of x as y. So then this function is really y is equal to 4x minus 5. Well, then what do? Well, for its inverse, we're just going to change the x's and y's. So for the y, we now write x. For the x, we now write y. So then we solve this for y. So add 5, x plus 5 is equal to 4y. Divide by 4, y is then equal to 1/4 x plus 5/4. And then call it f inverse. So this is f inverse of x is 1/4 x plus 5/4. So here I have x cubed minus 1, and quick check to see if it's one-to-one. X cubed is then shifted down to 1, so that's this function, something like that. And notice that it passes the vertical line test. It also passes the horizontal line test. So now we know that this function is one-to-one. So then we can find its inverse, which we write this as y is equal to x cubed minus 1. Then we just exchange x's with y's, and so this is then going to be x is equal to y cubed minus 1. Then we solve for y. So add 1, x plus 1 is equal to y cubed. What undoes y cubed? Well, that's the cube root, and so the cube root of x plus 1 is equal to y. So y is equal to the cube root of x plus 1, which then can be written as f inverse of x is equal to the cube root of x plus 1. So now we found that function's inverse. So we're given that the function x cubed plus 4 is one-to-one. We want to find these pieces of information. So it is one-to-one because it's x cubed shifted up by 4. And honestly, if we wanted, we could go ahead and graph this, shifted up by 4. And that's not perfect, but it's pretty close. Well, now let's actually find f inverse. Well, that is y is equal to x cubed plus 4. And so what we need to do is we need to exchange the x and the y. And so this is then x is equal to y cubed plus 4. Solve for y, minus 4 minus 4. X minus 4 is equal to y cubed. Take the cube root of both sides. Then I get that y is equal to the cube root of x minus 4. And that is my f inverse. So f inverse of x is the cube root of x minus 4. Well, since we're here, let's go ahead and graph this. And if you wanted, we could pick ordered pairs. We could pick some values for these things. Why not? Let's do that. But notice that all that's going to happen is this is going to reflect over the line y equals x. So I'm going to sketch in that line y equals x. If that's the line y equals x, if you flip this picture across that line, you will actually get the inverse cube root of x minus 4. And so here it might actually be easier to think about what a t-chart would look like for my original function and then just exchange those values. And so if I wanted to pick a couple values and plug them in, I could have picked, how about -2, -1, 0, 1, and 2. I would have then plugged these into this equation. -2 cubed is -8. -8 plus 4 is -4. -1 cubed is -1. -1 plus 4 is 3. 0 cubed is 0 plus 4 is 4. 1 cubed is 1 plus 4 is 5. 2 cubed is 8 plus 4 is 12. And let's confirm that all of these things work out exactly the same way when they put them back into the inverse. And so for the inverse, let's plug in -4. Well, if this is correct, we should get -2. -4 minus 4 is -8. Well, what's the cube root of -8? The cube root of -8 is -2. Okay, that's good. Let's check it again. Let's plug in this 3 we found. 3 minus 4 is -1. The cube root of -1 is -1. Okay, good. It's lining up. Then let's try it again. Let's plug in that y value 4. 4 minus 4 is 0. 0 cube rooted is 0. Look at that. They're matching up. Then let's plug in 5. 5 minus 4 is +1. The cube root of +1 is 1. And notice that we get exactly that. Then let's try 12. 12 minus 4 is 8. The cube root of 8 is 2. So then if I want to graph this, well, notice that these are just these reflection points. -4, -2, 3, -1, 4, 0, 5, 1, 12, 2, but that's off the charts. But then let's see what this looks like. Notice that although my graph is kind of bad, this should be smooth here. It is the mirror image of the purple one. So then let's answer our question real quick. What is the domain of f? Well, the domain of f, if you look back at this function algebraically, well, there's no issues. It's a polynomial. The domain of f is all real numbers. And then the range of f, well, if you look at the graph, this thing goes down forever and up forever, and there's no jumps, gaps, or holes. And so the range of f is all real numbers. Now, technically, what happens now is that when you deal with the inverse, the range of f becomes the domain of f inverse. Now, this doesn't make much of a difference because our domains and ranges are identical, but notice that they do swap. And so the range then becomes -∞ to ∞. And we've graphed it already, so we're good to go.